back to another Daishinfinity video. In this video, we're going to talk about the length of a function. The length of the function is given by the integral from a to b of the square root of 1 plus the derivative of a function squared with respect to x. Now, I would like to prove this formula by using a thing called Pythagoras' theorem and a Riemann sum. So keep in mind that I'm going to use those tools in order to prove the formula. First of all, we would have to observe the function. So we have a function on a xy coordinate. Let's take this one, call it f. And now we want to take the length of the function. So we want to take the segment and then see, okay, how long is it? If we would, somehow stretch this and into a line, and then you can just measure it from here to here, from A to B. Now, the best way to measure this one is to take 2 points. So we're going to make a secant line. Let's take this point here and another point here, and we're going to make a secant line that passes through these 2 points. Now we're going to talk about the segment over here. So we have this point and this point, and we want to know the segment over here. So now if this is the x coordinate and this is the y coordinate, this is going to be the width of x, so it's delta x, and this is going to be the width of y, so it will be delta y. Since we have a triangle with a degree 90 degrees in it, we can say that the hypotenuse is equal to the square root of delta x plus delta y and the whole component squared of them. Now, I would like to have a infinitesimal small segment of that part. So let delta x approach 0 and delta y approach 0. If delta x and delta y approaches 0, then delta x approaches dx, a small width dx, and delta y approaches dy. Now, if we want to talk about the distance, so the hypotenuse will be the square root of dx squared plus dy squared. Okay, now we're going to factor out the dx. So let's factor out the dx, not just the dx. We're going to factor out the dx squared. Now it will be 1 plus dy squared over dx squared. Now, every time you have something x squared divided by n squared, for example, it's going to be x divided by n, the whole thing squared. So we can tell this one to be d is equal to the square root of dx squared times the parentheses 1 plus dy over dx and the whole thing squared. Now, the rule of square roots states that we can take a square root of m times n and say that it's the square root of m times the square root of n. Since we have this one, we can cancel this 2 and the square root over here and say that d is equal to the square root of 1 plus dy over dx, the whole thing squared, times dx. Now let's put a box around it. And since we have this box around it, this is going to be the small segment of any particular function f of x. So if we take f of x and we want a particular segment here which is infinitely small, the distance or the length of it will be this formula. Now, I would like to have infinitely many summations of that formula. So let's consider d to be a function d of x. So depending on the x value, the segment length will also differ. Now, if we would consider taking the distance function, then we can take the distance values of each x values. So let's consider a distance function. So over here on this x value, it has this distance, and this distance somehow is another function. And now we want to take all of the values from one place to another. So let's call this place A and the end place B. So we are going to take A and B, for instance, for this function coordinate. Now, since we want to do this for d of x, we want to take the integral of the function d of x in some sort. So we're going to take infinitely many of them. So let's just write down the d of x again. And I'm going to write this in black again. So d of x is equal to 1 plus dy over dx, the whole thing squared, dx. Now, we want to have a segment A to B, and we're going to we want to have the segment AB, so the length between A and B, which will be B minus A, right? Now, if we would like to make an integral out of it, or take the whole values in between, we're going to take rectangles inside. So if you take the rectangles, we're going to take a certain amount of rectangles, and let's assume the amount of rectangles is the value n. So we're going to divide by n for each width of each rectangle. So the width of each rectangle is going to be b minus a over n. Now we have many of them, so the function value will be the rectangle surface area will be d of x times b minus a over n. I think I'm correct. And now we're going to take infinitely many of them. So depending on the xy value, we have to take the summation, where let's say I'm going to say xi, because let's say this is x1, x2, x2, x3, x4, and so on. So I will just tell the int xi, and let's say I is going from 1 to, let's say, n, because n is the number of rectangles we have. And since we have we have infinitely many of them, we want to have infinitely many of them. So we will take the limit as n approaches infinity of that one. And this expression will be transferred with this one. So now, I'll write the whole thing again. The answer to the length is going to be, the length will be the limit as n approaches infinity of the sum, or where I goes from 1 to n, of b minus a over n times the function d of xi, which will mean that we are going to put the xi in each of the x's. So it's going to be the square root of 1 plus dy over dx to the second power times dx. Okay, now the Riemann sum states that the limit as n approaches infinity of the sum where I goes from 1 to n of any function f of xi times b minus a over n, okay, times dx, some small dx, is equal to the integral from a to b of f of x dx. Since we have this one and this one, since we have this one, this one, this one, this one, this one, and this one is this part. So we're just going to write that part for the integral. So in the end, we're just going to write the integral from a to b of the function f of xi, which is going to be the function d of xi, which is just equal to the square root of 1 plus dy over dx, whole thing squared dx. Now this is the actual formula we get, but we know that if we take a quotient out of two segments y and x, it's just going to equal the derivative at a specific point x. That's why we can put this one inside here and we'll get the actual formula. So let's do this again. And now we got the whole formula. And now we can also put a box behind it because we have proven this formula. I hope you have learned something from this video, and I hope you'll subscribe to my channel, and we'll see us in the next Daishinfinity video. See ya.